He will speak about no, give me the program.
That's the title.
I know the title.
Ah, you know the title.
Virtual elements, and it's written also there.
Okay. Thank you, Mr. Chairman, for the nice introduction. And okay, this is a brief outline. And well, I will start with some brief reminder of virtual elements. I'm afraid that some of you already were in Edinburgh, or if they were not in Edinburgh, they heard Donatella yesterday. But you know, I thought that it was a little bit unfair to say, okay, you already heard about that, and I start assuming that you know. So I will, although briefly, recall the basic idea of virtual elements, and besides, you know, everybody has his own idea and point of view, and of course I like mine. Okay, and let's go. So let us start. I assume that I have an element, as you possibly already know. Virtual elements are made for dealing with polygonal elements, the decomposition into elements that are not necessarily triangles or quadrilaterals. So assume that you have a polygon, and you would like to have a degree of accuracy 2, and so you would like to have basically a space of polynomials inside here, define a space of polynomials. And of course, if you take all polynomials degree 2, there are 6. And if you want that this element can connect to neighboring elements, so you need to prescribe the value at each edge in order to assure the continuity. So the other side you will do the same. And of course, this makes 10 degrees of freedom, which is much more than 6. And so you have to do something. And the basic idea is that you take, essentially, you take functions which are polynomials of degree 2 on each edge. And that will make, you will fix 10 degrees of freedom. But then inside, well, you want all polynomials degree 2 to be inside. And so the simplest requirement is that, for instance, some elliptic operator of second order is constant. So with constant coefficient, you take could be Laplace operator, but could be something like this one, could be whatever, in a sense. So you fix 1 degree of freedom inside, and that gives you a space of dimension 11. And this space of dimension 11 contains all polynomials degree 2 plus other functions. So this is a very particular case. And let's see what you have on a more general case. And this is what we call the plain vanilla virtual elements. They were, in a sense, the first ones that were designed, and in a sense, this is the simplest one. So you choose your order of precision, k. Here again, the picture is for k equal to 2. And you will take Vk, which is made by all the functions which have a trace on each edge that is a polynomial of degree k, and with the Laplacian of order k minus 2. Okay. And then, okay, what can you do with those spaces? You see, we have seen that those spaces contain all polynomials degree k plus other functions. And in a sense, the name of the game is that you do not compute the other functions. So this is a sort of, well, not a religion, but almost. You know, in virtual elements, you do not compute the non-polynomial functions. So what do you do, since you have to manage them? So the idea is that you construct projectors. So typically there are two typical moves in virtual elements. When you don't know what to do with those functions that are unknown, in a sense, you only know the degrees of freedom, you project. You compute a projector onto polynomials subspaces. And when you don't know how to compute the projection, you integrate by parts. So these are the two typical moves of a guy working on virtual elements. So let us see some projection. So this is the sort of a projection in H10 semi-norm. So you look for a polynomial of degree k. You're given an element V of your virtual element space, which basically could the projection is defined for every element in H1, but you apply it to a virtual element, and then okay, you look, you say basically that the projection has the same effect as the true gradient of V. So you solve this, and now, okay, this is the matrix that you have to, say, invert. So this is a polynomial of degree k, okay? And this is the polynomials that you're looking for. It's also a polynomial of degree k, the unknown one. And this is the right-hand side, and V is unknown, but you know the degrees of freedom. So what do? You integrate by parts. So you take this guy here, you integrate by parts. This, you take the Laplacian that goes onto the polynomial, and this is on the boundary. And now each one of these two pieces is computable. Is computable if you know the degrees of freedom, out of the degrees of freedom. Well, the degrees of freedom will identify which is the guy in the virtual element space you're dealing with, and you use those information. This will be the average against the polynomial of degree k minus 2, and this will be the boundary values. Okay. So this actually does not give immediately V, the projection of V, this guy here. Because, of course, this matrix here is singular. Singular because the constant disappears. So you have to fix the constant, and in order to fix the constant, for instance, you define that the mean value of the projection is equal to the mean value of the guy that you project on the boundary. So on the boundary, you know, your guy is known, and so you can compute it. Well, then this is one projection, okay, on polynomials degree k. There is another projection that is very useful, and is the projection of the gradients of your element onto the polynomial of degree k minus 1. So you want to be exact on polynomials degree k, and so the gradient, well, basically you have two paths. You can take the previous projection and take the gradient of it, or you first take the gradient and then you project the gradient onto the polynomials of degree k minus 1, because you expect your projection to be correct when V is a polynomial of degree k, so the gradient of V is a vector valued polynomial of degree k minus 1, as this guy here. So this is computable, and of course I don't have to ask you how do you compute it, but if you just were not attentive before, you integrate by parts. Okay? So in order to compute this right-hand side, okay, this one, you integrate by parts, And then you have the divergence of a polynomial degree k minus 1, which is a polynomial degree k minus 2. You know the moments of V up to the order k minus 2. And this is on the boundary, so you can compute it. Perfect. So, and this is okay. This is, but, so you have at least 2 projections that you can use. Should be happy with that. However, what you would really like, for instance, is the L2 projection, you know, because when you have to integrate, say, V against a given function, or to do some computation on V, if you have the L2 projection, you are much better off. So just, you know, an H1 semi-norm projection is good, but not totally good, and the same for the gradient. Yes, of the gradient, of V. And, okay, if you want, you have the L2 projection of the gradient of V on pk minus 1. You might be interested in having the projection on pk, even though this, you know, the accuracy that you are after is k. So for the gradient k minus 1. Okay. So what do you do for that? Let's wait. Let us consider a model problem. Of course, you guess what is the model problem? It's Laplacian. Okay. So Laplacian with homogeneous boundary conditions. The simplest guy as possible. Okay, this is our problem. What is... yes, it was P. Okay, thank you, Mr. Chairman. You see, sir. Now, I'm sure, I mean, if the chairman is not your wife, you will just do not underline the mistake, you know? But if you are unlucky, and, you know, Elena decided, you know, that you should have as a chairman your wife, then you, PPU. Okay. Thanks, Mr. Chairman. So then, as you all know, you have a local stiffness matrix for the continuous problem, and which is split element by element, and that's the sum of it. And then you have a right-hand side, and you can write the problem in variational form. This is everybody knows, I think. Okay. So now you want to discretize it, and of course, with your virtual element spaces, and of course, in each element, you have to sort of construct the local stiffness matrix in your subspace. So, well, one possibility that in this particular case we are very lucky, because we already have constructed the projection, you know, an H1 semi-normal projection. So we can, instead of U and V, take the pinabla, the gradient of the pinabla projection for both of them, and this will give you a bilinear form on the space of virtual elements, which is a good mimicking of the true one. Well, this is one possibility. Of course, since here basically you have to put the gradient of U and the gradient of V, you know, in the continuous problem you have the two gradients. So I say, well, yeah, you have the projection of the gradients already. Right? Why not? So this is another possibility. So you can take the gradient and then the projection of the gradient. These are both two things that you can compute. And actually, in a sense, this is sort of the safer one. Both of them on this problem are absolutely equivalent. They give you essentially the same result. But, for instance, if you have a variable coefficients, so you will have some variable coefficients in here, I think it says you go down by 1, isn't it? Yeah. You lose one order of convergence if you take the other one. This one is safer. Okay. So this is, for instance, what you do. And what is nice is that what we call PK consistency, although I mean Doug will not like it, I don't know, but this is what we call is a PK consistency of the matrix. And then you have that this matrix here that you construct is equal to the true one that you should have applied on your space if you were able to manipulate the U and V, which you don't, then it will be exactly like applying to the two guys whenever one of the two is a polynomial of degree k. So in a sense, if one of the two entries, either U or V, symmetric, is a polynomial of degree k, when you do this, you don't make any mistake. But of course, this, the rank of this matrix, say for k equal 2, you have a rank 5. And you are in a space of dimension 11, and you should do something, okay? So the idea is that you construct the discrete bilinear form by taking the consistency part and then stabilizing. Well, tell you the truth, the choice of the stabilization is one of the pains in the neck of the method. Possibly the weakest point of the virtual element method is the choice of the stabilization. In a lot of particular cases and problems and so on, we know what to do, it works beautiful, blah, 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 blah. But as a general matter, if there is one point in which you staple, that will be on the stabilization, okay? So be careful with the stabilization. So the idea is that you have to put here something, and this, you know, in mimetic finite difference, you just you wrote something like, you have to put any bilinear form, symmetric and positive definite bilinear form that does not hurt what you do here on polynomials degree k. And now in virtual elements is essentially the same idea. You apply something on the difference in between your virtual element and its projection. And of course, if your virtual element by chance is a polynomial, the stabilization will not play. This is fundamental. So the idea is that your stabilization should not act on polynomials, because on polynomials you already know that you are correct. Your bilinear form, if one of the two is a polynomial, is the right one. You don't want to touch. So you want your stabilizing term to act only, let me say, the non-polynomial guys, okay? And one possibility is just what you know about your guy here. Well, you know the degrees of freedom. This is for sure, that you know the degrees of freedom. So if you apply the degrees of freedom applied to the difference in between your virtual element function and its projection, if by chance your function is a polynomial, this is 0. Okay? So this bilinear form here will vanish whenever either u or v is a polynomial degree k. So when you sum it to the previous part, the A consistent, then you have a bilinear form, which is now, if you have a problem like red is positive semi-definite because the constant will still break your balls, but, sorry, to still be a pain in the neck, but basically you have a nice matrix here, which is exact on polynomials. If one of the two is a polynomial. Okay. And then, of course, when you sum up all on the whole domain, you will have now the fact that you are sort of elliptic on the gradients. When you sum up on the whole domain, you have the boundary conditions, and then you will have positivity for the whole matrix. As it happened with finite elements, okay? You have the local matrices are not positive definite, but when you sum them up, become positive definite. Okay. So, well, we have a method. Okay. We have a method, and okay, I'll tell you, you believe me, you should. And it converges with order k. Of course, if the solution is smooth enough. But, okay, if you compare essentially with finite elements, we have seen that for k equal to, remember, we need inside the moments up to the degree k minus 2, which is 0, so the mean value. So you have 1 degree of freedom more with virtual elements than with finite elements. And if you go to degree 3, then you have here you have 3 guys, and here you have 1. So, okay, you pay more for basically the same stuff. And, well, on quadrilaterals, it's not so bad. It's not so bad, but, for instance, you know, these quadrilaterals, you might, with finite elements, do some trick in order to get rid of some internal degrees of freedom. Here, well, we will. Actually, the whole lecture is dedicated to how to get rid of the internal degrees of freedom. So this is what we do today, okay? We try to get rid, as much as we can, of all the internal degrees of freedom. Okay. So, in order to get rid of the internal degrees of freedom, we do the most stupid thing that you might think of, is that you increase the space. So come on, you have to decrease the space. Then, okay, I will. But first, I will increase the space. And the idea is, you remember that before I had, say, take again k equal 2, okay? You have functions which are p2 on each edge, and Laplacian was in p0, constant. Now, Laplacian in p2. Okay. And then, so the degrees of freedom will be the values at the vertices, the value at the midpoint of the edges, and the moments up to the degree 2. So you have 6 internal degrees of freedom instead of 1. Well, good. But in this space, however, I will be allowed to take, say, the L2 projection onto pk. So I have a lot, with those degrees of freedom, I have a lot of information more. So in a sense, I like it. You know? When I have to do computations, so it's good, but it's very expensive. Come on. So this is essentially, this is the dimension, you see, as I said. You have 6 degrees of freedom. And you have to do something. So now comes the trick, okay? Next slide is the slide, okay? So that's for k equal to 2. Then we will take higher k. So you build another projection onto the polynomials degree 2. And the idea is, we will see it better in a while, is you want that your projector uses as few degrees of freedom as you can. So remember, you have a lot of degrees of freedom. And you say, okay, let's see. I'm given one guy here, V, and I know its boundary value. Now I want to construct a projector, which will not be the orthogonal projector, of course, but a projection that will give me this p partial 2v, which is a polynomial degree 2, which essentially is the projection of v. The boundary values of this guy are the projection of the boundary values of that guy onto the traces of the polynomial degree 2. Well, is it enough? Will the matrix be non-singular? Well, okay, if the matrix is this guy against this guy, and if you get a 0 is because the two or one of the two is identically 0. But there is no polynomial of degree 2 which is identically 0 on the boundary. Haha. So that's well defined. It's perfectly well defined. This matrix here, 6 by 6, is non-singular. No matter what is the shape of the element. Remember that what we have in mind, most of you have seen the horses yesterday. So we have in mind elements that could be horse-shaped. So we want to make arguments which are valid for very general shapes. But this, okay, this is perfectly well defined. Then, okay, once you have a projection onto P2, you say, okay, all the other degrees of freedom that I did not use, I will take out of the projection. So I will take an element whose, say, lacking degrees of freedom are given by the values of the projection onto P2. So basically, the new space that you have will use your new degrees of freedom will be only the boundary values. Because once you know the boundary values, you can compute this projection. And then you can compute all the other degrees of freedom. So your degrees of freedom are the boundary values, only the boundary values, but you will still contain all the polynomials degree 2. Because a polynomial degree 2 will have the projection on the boundary will be the trace of himself or itself, and so it will stay there. Wow. So you got rid of this nasty degrees of freedom inside. Okay, it looks like, well, of course, the first time you think about it, you're like, come on. You are, doing what in Italian is il gioco delle tre tavolette, on the fear, the guys like this guy, okay? Okay? I say, come on. You are cheating, In particular, if you are Italian and you present a trick like that, everybody will laugh. But, okay, maybe it really works, It's, so you see, it's hard to believe, but it does work, you see? Okay, now this is a little test. Donatella showed it yesterday to see that with k equal to 2, not only we can do it without internal degrees of freedom, but we can afford some non-regularity of the mesh. And this was this. I remember the first time we tried this from the paper by Doug and others. We say, okay, so this one that's for serendipity Q2 doesn't work, and then with our methods it will work. And then it will work for both. I say, oh shit. It's written that it doesn't work. And actually we were so dumb that we took a generic smooth function. While, the counterexample is smarter than that. It's not just a generic smooth function. It's carefully chosen. And actually, with that exact solution, the serendipity Q2 does not work, while the serendipity them does work. Okay. Then, well, I did it for k equal 2. Why can't I do it for a bigger k? Okay. So okay, let's try k equal 3. It's a little step. So I want again compute a projector which uses only the boundary degrees of freedom. Well, it worked before. Now, try again the same stuff. And, well, you see that the argument, there is no polynomial degree 2 that vanishes on the boundary of a polygon. That was correct. But there is no polynomial degree 3 that vanishes on the boundary of an element. Well, if the element is a triangle, man, you are in trouble. Because you have a polynomial degree 3 that vanishes. And so the idea is that you have to say add some internal degree of freedom, like a mean value, and you will have, since you don't know whether your element is a triangle or not, you have to take a least square solution. Okay. Well, and then so you define again this projector, and once you have defined the projector as before, you take all the degrees of freedom that you did not use and you evaluate on the projection. Okay. And okay, now, well, with 3 I survive with this least square projection. Now I want to go up, as in Italian we say l'appetito vien mangiando. You start eating and your appetite grows, So we had 2, k equal 2, k equal 3. And so what for a bigger k? Well, the bigger k, you see the crucial point was a polynomial that is identically 0 on the boundary. If you want to use only the boundary values, the trouble comes from polynomials which are 0 on the boundary. And so you start by deciding, okay, what is the minimum number of straight lines necessary to cover the boundary? So which is basically the minimum degree of a polynomial which is 0, non-identically 0, but 0 on the boundary. So if you have an element like this, okay, this is 6. Okay? The lowest order polynomial vanishing on the boundary is degree 6. But if you have this guy, remember in this guy, this element, okay, is a triangle, but for us it has 1, 2, 3, 4, 5, 6 edges, which by bad chance are aligned. So the number of edges here is 6, is convex but not strictly convex, so to speak. And you can cover the boundary with 3 lines. But and if you are not convex, this could be even worse, because here you can cover, it's not a triangle, but this line here covers the 4 of them, so you can cover the boundary with 5 lines. 1, 2, 3, 4, 5. And okay, and if we really want to work, with horses or crazy shapes, then what about those ones? Okay, yeah, about those ones, you see that here you have, you don't even have aligned edges. Because, the first idea is you do your code, you follow the boundary, and you look at the angle. And if when the angle is flat, here is a, but here you cannot play the game of the angle. All the angles are different from pi. And you can see that, here you can cover the boundary with 8 lines. 1, 2, 3, 4, 6, 7, 8. Huh? And okay, so what to do? Well, essentially, okay, I got one step back. If eta is bigger than k, then you can use a projector that uses only the boundary values. Otherwise, you have to take some degrees of freedom inside, as we did for k equal to 3. And but then, to really choose the least amount of degrees of freedom inside, it could be really complicated. So essentially, we decided that we could consider 2 typical choices that we called the stingy choice and the lazy choice. Well, the lazy choice with the, okay, listen, I don't want to know the shape of the guy, of the element. It's surely, I treat it, the worst case will be that k is equal to 3 is a triangle. So I will treat it as a triangle. So I will add as many degrees of freedom inside as I would on a triangle, which is, say, the maximum. And the other one is saying, no, I don't want to spend money for that. So I want to go and check. I could look at the matrix, see what I go down, I add the degrees of freedom one by one until the matrix becomes non-singular. So, and this is the stingy choice. And of course, the decision among the two will depend very much on how many times you have to do the computation. Because, in some cases, for instance, when you have the snapshots, and you solve the problem for many values of the parameter. Many means 20, 30. So you solve the same problem for 30 values of the parameter, and then you use this reduced basis trick. Or in other cases, in which you have to do some optimization, and you will do a lot of computation on the same grid. So if you have to do a lot of computations on the same grid, maybe it's worth paying a lot on each element, and you have strangely shaped elements. It is worth to afford the cost of taking the stingy choice. If otherwise you have to solve it once, okay, you go. And okay, let us see what we can do. So first, we say on quads. We take the same example that we had before on quads and see how it does. Well, on quadrilaterals, those ones you remember, they were non-degenerate. They were non-degenerate quadrilaterals. They were not triangles. So you could take the stingy choice. And you have, we compared, since we were on quadrilaterals, we compared, this is the stingy choice, and we compare with Q3, Q4, I mean the finite elements. Finite elements without serendipity. And you see, basically, you lose a little bit, This is, the finite elements, and then you lose a little bit, but of course, nothing to see with what you will lose in finite elements trying to do serendipity. And then you say, okay, since we are virtual elements, we can take a mesh like this, and then we were lazy, we took the lazy choice, and no, we also take the stingy because they are convex, okay. And so here you do not compare with finite elements because you cannot do finite elements on those polygons, but you can see that basically the classical VEM, without reducing the internal degrees of freedom, or the two types, okay, you do the lazy choice, you lose a little bit, you do the stingy choice, still, I mean, there is no real gain, okay? And so basically the three of them work very good. Okay. So now very quickly, something on three-dimensional decompositions. On three-dimensional decomposition, the idea is that you would like, what is important is really to get rid of the elements on the faces. Because so far in 2D, you could have objected, why do you struggle to eliminate the internal degrees of freedom in 2D while static condensation would do it for you? And several codes do it more or less automatically. You don't have to do the static condensation yourself. When you go to 3D for faces, then is a different matter, because you know the static condensation, if you have the phase degrees of freedom, that they see two elements, you know, so it's more complicated. So it will increase the sparsity, lose the sparsity of the matrix. So okay, it's and we took some examples. We took this problem now with variable coefficients, and we took three. I think that Donatello already showed those meshes. One mesh was to test, compare just in cubes. Okay, and this is CVT, centroidal Voronoi tessellation, and this is random Voronoi. This is so those are okay polygons, but a little bit rounded up, and those are blah, 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 blah. Okay, and then okay, here are first. So we cannot compare with finite elements. So we compare the three meshes for different values of k's. And you have for the structured mesh in cubes, the centroidal Voronoi tessellation and the random tessellation, and you have the H1 error and the L2 error, and you see that every guy behaves as it should. Okay, okay, and this is now a comparison. Since we still have convex guys, a comparison in between the non-serendipity virtual elements and the lazy choice. And you see that, okay, it's you still have basically they are superimposed, okay? As a 3D, for instance, 3D VEM and 3D VEM lazy, they are basically the same. So you don't lose too much by the lazy choice. You don't gain too much because it's the lazy choice. So you keep, but you don't lose too much. Okay, now, okay, the same idea could actually be applied to other type. These are, the conforming H1 elements. You could apply the same idea to HDiv, HCurl, C2, C1 elements, and so on. The idea is always the same. Okay, you take a bigger space, you compute you design a projector that uses less degrees of freedom, and then you compute the other degrees of freedom with the projector. And now there is one thing which is important, however, is that if you are dealing with exact sequences, in virtual elements, typically what we compute with scalar, H-curl, H-div, and so on, they form, you can easily behave in such a way that they will form an exact sequence. When you do serendipity, okay, you have to be careful, design the projectors carefully, because otherwise you will not go into the right space. So it can be done. We did is written, but is not the first And then, okay, these are general considerations on virtual elements, and it contains more or less I say that, well, this is important. We don't have a reference element, okay? This is the main difference with respect to finite element, no reference element. And so it requires a bigger effort, but is much more powerful, and already on quadrilaterals and triangles, so it can give you better. Okay, that's okay. Thank you very much. Yes. Yeah. Well, I mean, I say that at the beginning we misbehaved and the results were good. Okay, so it's clear that the whole idea of what was designed there was to make the result to be bad. Right. Yes, yes, okay. No, but what I said was that, you know, the construction of the counterexample was smarter than one would think, just by choosing, it was a compliment, not a criticism. I'm sorry? Okay, but you know, it's anyway, I just wanted to say that we didn't have a paper that was proposing the serendipity as the right way to compute on general quads, because it's not. No. It's, okay, I thought that I made it clear by saying that the paper, the function, the mesh that you choose was to make a counterexample. Okay, this is. Yes, sure, but
so the VDM, sometimes you have more freedom you want to get rid of. Is that why the few degrees of freedom will always be better? You have to think about how to solve the discretized system in the end.
Yeah, I know your point, yeah. I agree with that, and I remember that we discussed that in Pavia, and you had very nice examples in which, I don't know if you will present it, I don't want to spoil. Are you talking about that today? No, okay.
I kind of like the inflation, not the deflation.
Yeah, but he presented in Pavia a very nice example in which by taking a system and increasing the dimension of this, making it more singular, you and then apply the preconditional conjugate gradient, you had better results. So I mean that was a very nice. So I know that. You taught me. But the idea is that if you want, you can. You see, that's the whole point. You know, if you want to get rid, to have less degrees of freedom, you can do that. No, okay, yeah.
Okay.
Okay.
If there are no more questions, thank you again.
Okay.